All right, welcome everyone. Today, for today's keynote seminar, we're really happy to have Leo Radzihovsky joining us from Boulder. Leo is an expert on effective theories for soft modes used in a variety of contexts. He's also had a lot of recent work, interesting work relating fractons to theories of elasticity and dislocations. And today he's going to talk about quantum smectic gauge theory. Go ahead, Leo.
Yeah, thanks for the introduction and for the invitation to speak. It's a real pleasure to be speaking this venue, even if only virtually. We always lament of how much good fun time is being missed, especially at places where there's a lot of good friends, like in University of Chicago, where I still have fond memories being a postdoc with Paul Wigman and working with Sasha Abanov in the mid-90s. Anyway, well, it is what it is. Hopefully, we're about to get rid of both of our viruses very soon. So I'd like to tell you about some recent work that I've been doing. Initially by myself with in a work that appeared in PhysRev, and then more recently there's an article on the archive that appeared today with my very talented student Zheng Zai. Okay. But in a form of introduction, before I delve into the subject, let me just start with just sort of some basic background and remind you that, most states of matter that we deal with, states of at least bosonic matter, follow so-called Landau paradigm. These are so-called conventional ordered states that are characterized by a local order parameter, and they are described by and classified by different patterns of spontaneous symmetry breaking. And in the modern parlance of entanglement, they are for quantum states, they exhibit short-range entangled ground states. However, much of the field, at least in quantum condensed matter physics, has been in the last 30 years, probably, maybe even longer, has been focused on so-called quantum liquids that go beyond the symmetry breaking paradigm of Landau. And so these states are locally look the same and therefore don't admit a local order parameter, Landau order parameter that can distinguish them. But nevertheless, they're non-trivial quantum liquids that exhibit non-local fractionalized excitations at the end of strings. They also exhibit topological order of order 1 ground state degeneracy on non-trivial manifolds with non-trivial genus, and they are long-range entangled. So these kind of states are well described. We've gotten used to them, very well described by so-called gauge theories. And so here's an example of a toric code in 2 dimensions where there's 2 types of excitations: electric charges connected by electric field lines and magnetic charges connected by magnetic field lines. And they have non-trivial statistics, mutual statistics. So this is up until about maybe 5 years ago, this was the most theories fit into this paradigm. But more recently, like I said, maybe 5 years ago, there's been a discovery of class of phases, a class of models, sort of new class of quantum liquid models, so-called fractal quantum matter, that have drastically different, qualitatively different properties that do not seem to fall into the paradigm that we've gotten used to in so-called conventional quantum spin liquids. And I should say, even though most of the activity in this field dates back to the last 5-6 years, really to my knowledge, the first paper that wrote down a model that exhibits the properties of models that we now call fractal models, it was done by Claudio Cimone in 2005 in a very beautiful paper. So what are the exotic features of these models. And needless to say, so far, there's no really at all experimental realizations of these systems. Even theoretical sort of ideas of how to realize them are still sort of at the forefront and are being discussed, but there's no really a good, simple models that are proposed to be realized experimentally. So much like conventional spin liquids, they exhibit non-local fractionalized excitations, but those excitations have restricted mobility, and that's kind of one of their key features and most prominent features. They also exhibit exponential topological degeneracy on a non-trivial manifold rather than degeneracy of order 1. And they're believed to go beyond topological quantum field theory description. So the restricted mobility appears in a variety of ways. So there are excitations called fracton excitations that are simply, even though this is a translationally invariant system, these excitations simply cannot move. And so if you force them to move, you have to supply extra energy to create an additional quasi-particles, additional fracton quasi-particles that you're forced to create due to the structure of the Gage theory, or due to the structure of these models. There are other kind of excitations that we call planons and linons that have just restricted mobility. They move either confined to move either to a plane, in a plane, or in the one-dimensional subspace of the full three-dimensional space. So many of these models, and there's been an explosion of them. I can't even keep track of all the models that have been written out. Are typically some kind of a Z2 fractons. There are lattice models of qubits on the three-dimensional lattices. But there's a sort of a complementary description of another class of fracton models that is described by so-called tensor gauge theories. These are gauge theories, U1 symmetric tensor gauge theories that have been studied prior to the new field of fractons, and they've been known. They're understood quite well, and they're basically you generalize vector electric field and its canonically conjugate vector potential to tensors, symmetric tensors. They still obey a canonically conjugate commutation relation. And the Hamiltonian, simplest sort of model Hamiltonian, will have E squared plus B squared, like in ordinary electrodynamics. The new key feature that appears very naturally, for example, in the scalar charge, so-called simplest version of these tensor gauge theories, is the scalar charge theory, where the Gauss's law is a double divergence on both indices of the symmetric tensor electric field. And so these theories were known, and there was not much interest in them in condensed matter community until Michael Pretko, as a graduate student in 2016, pointed out that this simple generalization of Gauss's law immediately implies not only a conservation of charges, but also conservation of dipoles. And that immediately implies the fracton constrained dynamics. To see this is very simple and very beautiful. If you have a fracton charge appearing here in this Gauss's law, if you try to move that fracton charge, that motion really corresponds to adding a dipole to that original fracton. So addition of a dipole to a quasi-particle is a motion or a hopping of that particle by a lattice constant. And so if dipoles are conserved, as encoded in this Gauss's law, then that process is not allowed. It's forbidden by the Gage theory. And as a result, the only way you can move a quasi-particle, a fractonic quasi-particle, a charge, is by adding an equal and opposite dipole. And that process generically is allowed if you inject some energy into the system, but to the extent that these dipoles are gapped, and this is not possible unless, on shell. And so then charges are immobile. On the other hand, if you look at dipoles, depending on which versions of the theories you study, there are many various varieties, these dipoles can move as a pair, but they do have restricted mobility. They often move perpendicular to the dipole moment, or sometimes along the dipole moment, depending on the detailed nature of the theory that you look at. Okay, so this was a sort of the status in 2016, and I sort of listened to many talks on fractals at that point, and realized and got reminded of something that I was aware of in the theory of elasticity, that these restricted mobility reminded me quite strongly about restricted mobility that one finds in dynamics of topological defects like dislocations and disclinations in two-dimensional crystals. And so in fact, I was lucky enough to have Michael Pretko come to Boulder for 3 years as a postdoc. And I shared, when I returned from my sabbatical, I shared some of these ideas and conjectures about the relation between elasticity and these tensor gauge theory with him. And we developed a dictionary, so-called fractal elasticity duality, between topological defects in the phonon fields in the crystal, in particular in 2+1 dimensional crystals, so quantum crystals, and the fractal symmetric description, symmetric tensor gauge theory description of fractons. So this dictionary is given here. So the double curl, the well-known double curl condition on the strain tensor UKL that gives you disclination density is in fact translates into a double divergence of the tensor, symmetric tensor electric field. So the fracton, disclinations in the crystal then map onto fractons. The dipoles of disclinations, namely dislocations, map onto the dipoles of this tensor gauge theory. Phonons correspond to gauge modes. Strain tensor is maps onto the electric field tensor. The momentum maps onto the magnetic field. And there are these nice correspondences where the Newton's law, momentum conservation in the crystal, maps onto a Faraday law, is realized as a Faraday law in this in the tensor gauge theory. So this is one component of the introduction to the subject that I wanted to cover before I delve into the subject. But the other component is yes.
Yeah, I just had a question about what you mean when you said that there isn't really a proposal to realize these things experimentally. Does it mean that these models, these typical fracton models, are kind of fine-tuned and unstable to perturbation?
I would say they're quite robust. If you're sitting in a phase in which, in a fracton phase, then like conventional gauge theories describing spin liquids, they're quite robust, but they're less robust in that they also rely on a geometrical structure. It's not purely topology. But so from that point of view, one can imagine thinking about models that are not exactly these exactly solvable fixed point models that people are studying, like the Haas code or the X cube model, and thinking of them as some limiting case of some more generic models. But the problem is, at least taken at face value, at least the lattice models are all involve highly, many spin interactions, like 12 spin interactions. On the, the spin sitting in the qubit sitting in the cluster on bonds of some structure, extended structure in 3 dimensions. And so the kind of terms you have are these commuting projector terms that are a product of these Pauli operators. So I'm not aware of any realistic proposals for realizing those lattice models, although there have been some discussions. I would argue that, for these other class of fractonic models, namely these tensor gauge theory realizations, I would say that, and in part, this was a motivation for our work, is that 2+1 dimensional crystals, I would say, quantum crystals are in fact a realization, direct physical realization of these systems. Okay. But one would like to have more.
Can I ask a question about the elasticity slide? Is that just a translation, or is there really some duality going on there? Like, are all the fields local with respect to each other on both sides?
It's a duality. It really is a duality, and I will get into it more. I will talk about a complementary way of looking at this duality, which is more appealing to me, which is going to be coupled vector gauge theory duality. But it's really kind of at a coarse level, sort of squint your eyes level. It's really like a vortex, boson vortex duality, or XY abelian Higgs model duality, but with a flavor. So I'm kind of getting ahead of myself a little bit, but if you think of phonons as Goldstone modes, they are, unlike an XY model, we have a single Goldstone mode for superfluid phase. Now you have multiple Goldstone modes, one for each direction that you spontaneously broke translational symmetry along. And so now you can loosely think of elasticity as some kind of a strange coupled XY models. So those coupled XY models then can be dualized in the same way you dualize a single XY model into a gauge theory. But what emerges is not a conventional vector gauge theory, but a tensor gauge theory.
Leo, I have one step back.
Okay.
To complete the vocabulary, disclinations and dislocations are characterized by Burger's vector and Frank vector, right? So how they are translated?
Well, so literally it's given here. So the charge of the disclination, which is this deficit angle that you get by doing the line integral around the disclination, is precisely the charge that you get in the tensor gauge theory. That's a scalar. On the other hand, dipole has a direction, and dislocation has a Burger's vector that's perpendicular to that direction. So if this is the dipole P, then the dislocation B is in this direction. It's perpendicular to this.
Mm-hmm.
It's just a simple 90-degree rotation, but you can see it in this picture right here. So here's the dipole of two disclinations, and the Burger's vector, if you look carefully, is actually perpendicular to it.
Yes. Okay. Fine. Question. So if we come back to the Hamiltonian, it was on the previous slide. Right. If I take this Hamiltonian in face value, the physical characterization of disclination and dislocations are these two vectors. So the Hamiltonian must be rewritten somehow, maybe non-locally,
right,
but
yeah,
in these terms.
Yeah, you're absolutely right. So this is just in the form of introduction, which is why I'm skipping all the details. But strictly speaking, there's a vector potential dotted into J, Ij, that couples to the dislocation or dipole current in the way you used to. And so, and there's also A0 couples to rho like this. So there's these gauge fields are now produced by dislocations and disclinations. There are dislocations or dipoles and charges, as in a conventional gauge theory, are sources for these electric and magnetic fields.
Yes. So the origin of my question, I understand that. The origin of my question is the following: elasticity could be also non-locally rewritten through Burger's and Frank vectors, right?
Mm-hmm.
It could be ugly, but it could be really.
So sure. So if you were looking at, you're absolutely right. So to give some intuition, imagine you integrate out phonons and you write down a Coulomb gas of dislocations and disclinations describing a crystal. That Coulomb gas will have some kernels, long-range kernels. You can think of those kernels as produced by the scalar components of this tensor gauge theory. So in other words, if you went to the classical limit, electrostatic limit, then the long-range interaction between topological defects in the crystal, you can think of as the scalar potential, as produced by the scalar potential, electrostatic potential of this more general quantum tensor gauge theory.
Right. So basically, the thing which the thing which I want to understand, maybe I'm jumping ahead, is that what I hear is that operator content or degrees of freedom content of the elasticity theory and of that stuff are equivalent.
That's right.
But the Hamiltonian, the energy may not.
No, the energy is as well. You literally derive this Hamiltonian from the Newton's laws describing a crystal.
I see. So the energy is also elastic energy, right?
Yeah, the energy is really capturing the elasticity and topological defects, the whole thing.
Right. I see. So therefore, it's fully equivalent.
It's fully equivalent. It's a duality.
Elasticity, just another description.
Just so that's in the same way that, you know, if you take an XY model of bosons, describing bosons, quantum XY model in 2+1 dimension, that maps onto a vector gauge theory where the charges are the vortices and the gauge fields describe the currents, if you wish.
But then why did you say that there is no experimental realization?
Well, because I don't want to. In my response to Luca's question, in fact, I said that, you know, part of the motivation is that this, if you wish, this is one realization, one and only realization of fractonic matter. On the other hand, it's not there's some deficiencies, so there's some, you know, much of the focus on the subject of fractons is on lattice models of qubits, because the original motivation was, for example, for topological quantum computing and for robust finite temperature quantum memory. And so when I was referring to there's no physical realization, I was referring to the lattice models, not to the gauge theory realization. If you wish, there's these two classes of fractonic matter. One is in terms of these tensor gauge theories, and one is in terms of lattice models. And the lattice models are the ones that, of qubits, these gapped fracton models are the ones that I was referring to.
Okay. But for simplicity, for myself, I will be thinking about just elasticity.
Just elasticity, sure. This is a reformulation of elasticity that's convenient, if you wish. Now, its utility is another question. You know how useful it is. What do you learn about elasticity, or what do you learn about fractons from the elasticity side? That's still to be discussed and thought about. And you can be a judge for yourself. So the other component of what I want to talk about is, I'm looking at the clock, making sure that I'm not totally behind, but is the quantum liquid crystals, and in particular quantum smectics, as that's what's so. I should say, look, you can take this theory, and we have this observation of this duality in many different directions. And we've been exploring this in the last 2 years. But one direction, which is my recent interest, is thinking about quantum smectics. And you can think of a quantum smectic as something, or more generally, quantum liquid crystals, is something you get by quantum melting a crystal. So when you melt a crystal into a smectic, you get a structure which has some elasticity in some direction and has a liquid-like correlations in the other direction. More generally, you get some kind of a layered structure. You get a layered structure of matter, quantum matter, which is periodic maybe in one direction, but translationally invariant in another direction. And so one might want to ask, what happens to the fracton like restricted mobility that one finds in this mapping of duality, using these dualities, when one applies it to these more intermediate states of matter like smectics, and what one can learn about the system in either direction. And so there are many, I've listed here a slew of physical realizations of quantum smectics, and so that they provide a nice motivation for actually thinking about this beyond models, but really about physical systems. These are partially filled, half-filled Landau levels systems where one observes an enormous anisotropy, resistive anisotropy, as was done by Jim Eisenstein long ago, I guess in the 1999, and has been studied extensively. One can think about spin density wave, charge density wave, and pair density wave, where layered structures often appear. One can think about imbalanced Fermi gases, where one proposals have been made about emergence of a FFLO-like states, which are, you can think of as a pair density wave of sorts induced by a Zeeman field. And of course, there's many kind of layered structures and all kinds of mesoscopic ordering that happens in a frustrated magnets, helical magnet. So, okay, so with this background, what I want to do is now tell you a little bit more focused about applying this and thinking about this in the context of a quantum smectic. So I already discussed the tensor gauge theory, crystal elasticity duality, or at least I've stated it. And so now what I'm going to do is talk about an alternative formulation to this tensor gauge theory duality in terms of, namely, duality in terms of vector gauge theories, which is more appealing because vector gauge theories somehow we have more intuition and more experience with. So I will start out with that, and then I'll turn my attention to the quantum smectic and formulate its dual, gauge theory dual, and then I will use that to formulate and describe a crystal to smectic and smectic to nematic phase transition in terms of a Higgs transition between these phases of matter. So it really provides a fully quantum mechanical description between a crystal and a smectic and a nematic. And sort of the kind of things I'll be interested in is summarized in this figure. We'll be able to go from a crystal to a smectic to a nematic. And in particular, I'm interested in formulating, as a new formulation, formulating this quantum dual gauge theory of a quantum smectic. Okay, so as I said, so this tensor gauge theory description is nice and it's stimulating, but it's somewhat of an unfamiliar beast working with symmetric tensor gauge theory. So in fact, when I first thought of this duality, or conjecture this duality, my first thought was actually thinking of elasticity as a XY model, as I was explaining when I was answering Michael's question. And so one might, one is reminded of XY model where XY model dualizes, XY model describing quantum bosons in 2+1 dimension dualizes to a conventional vector gauge theory with gauge charges coupled to the gauge fields, to the vector gauge fields, through the conventional current vector potential coupling. So then if one squints his eyes and thinks about elasticity, where there's now two Goldstone modes in 2 dimensions, then one can think of the elasticity theory as some kind of a flavored XY model, where there's just 2 flavors of bosons that I label by K. And so then what one would get is, naively at least, is 2 sectors of vector gauge theories, and those do not have charges of those theories, clearly do not have fractons because they're just conventional vector gauge theory. So one has to look at it a little bit more detail, and looking at it in more detail, one realizes that elasticity is actually formulated in terms of symmetric strain tensor. So what appears is not just DI-UK, but there's also its partner DK-UI. And one can think of this, or the way I think of it, as a spin space coupling. If you think of K as flavor and I as space, then normally if there was an independent spin space symmetries, let's say rotational symmetries, then there wouldn't ever be a term that has I and K talk to each other, space and spin talk to each other. But in elasticity, indeed they talk to each other. And that's essential to encode rotational invariance in the target space of the whole crystal. You can take a whole crystal and rotate it in the target space, and that's encoded by the fact that only symmetric component of the strain tensor appears in the elasticity theory. So, and that naturally brought us to the symmetric tensor gauge theory that I described before. But one can naturally ask whether is it possible to formulate an equivalent vector gauge theory of elasticity. And indeed it is. And the first crucial step is to rewrite this symmetric formulation in terms of symmetric strain tensor in terms of an coupled XY model. So kinetic energy is the same. This is just the momentum, the kinetic energy. And then what I do is I rewrite this object in a very simple form. I take a non-symmetrized strain tensor, di uk. So simply as it would appear in the XY model, flavored XY model, and I gauge it by theta times epsilon ik, where ik is the antisymmetric tensor, just an full antisymmetric tensor, -1 and -1. So what is theta? Theta, in fact, is the bond angle of this crystal. And so what happens is that if you look at low energies of this theory, in fact, it's equivalent to the low energy of this theory, simply because if you think of if you're from gauge theory background, if you think of theta as a gauge field, it Higgses out in the low energy limit, it Higgses out antisymmetric component of this unsymmetrized strain tensor, di uk. And what it leaves for you is just the symmetric component. The antisymmetric component corresponds to Locke of the bond angle to the rotation of the crystal. And of course, once you want to treat this, you want to have a fully quantum mechanical theory. So this theta now, you can write down an XY model that, like a rotor model that describes this theta degree of freedom. This is just the bond, XY model corresponding to the bond degrees of freedom. And they're coupled in this funny way. Okay, so but now what's the appeal of this over this description? Well, now I really have 3 XY models. I have an XY model, one for each phonon degree of freedom, UX and UI, and I have an XY model for the bond degree of freedom, and they're coupled in this minimal coupling way. So using this, here's the rewriting of what I just said. One can simply dualize it and turn the crank of the conventional boson vortex duality and get out from this elasticity theory of 3 coupled XY models. One can get 3 vector gauge theories. There are 2 vector gauge theories, capital vector gauge theories, E sub k and A sub k. And then there's the other sector is the little e and little a sector, but the magnetic field in this little a sector is not gauge invariant. It's actually minimally coupled to a 2 form, namely the antisymmetric part of this AK object. And then there's a natural, these gauge fields are naturally sorted by dipoles or dislocations. And there are 2 types of dislocations, let's say, on the square lattice, and by disclination currents. So this is the statement of the vector gauge theory, coupled vector gauge theory duality of that describes the underlying 2 + 1 dimensional quantum crystal.
Leo?
Yes?
I have a question. So when you gauge theory means some local symmetries, which means that certain fields are not really physical, but being introduced.
That's right.
Make things local. What symmetry
is local in the crystal? Yeah, it's
what's the local symmetry? So look.
Yeah, so it's very simple actually.
Just let me ask. Crystal doesn't have any local symmetry. It's a crystal. As well
it's very much like saying E and M doesn't have any local symmetries if it's formulated in terms of electric and magnetic fields. But if you go and formulate in terms of vector potentials, then all of a sudden you've made your description more appealing, maybe in more amenable, particularly in quantum mechanics context when you have to couple it to matter. But and so by thereby you introduced a local redundant description. So the same thing happens here. If you take a strain tensor, Uij, Uik, it's diuk. And so this object, if I think of it in terms of the strain tensor, well, sorry, let me say it differently. If I write down a continuity equation for the momentum continuity equation, namely time derivative of the momentum plus divergence of the stress equals to 0. So this is written in terms of physical variables. Momentum and stress is just Newton's equation. But suppose I want to solve this equation. One way to solve it is to introduce gauge fields, which are redundant description for the stress and momentum. They're convenient description, much like in electrodynamics, and they're a way to solve this current continuity equation. So it appears in exactly the same way here. So this is how it appears in elasticity. So when you solve elasticity equations, if you want to deal with elasticity in the presence of topological defects, you often introduce, I'm blanking on the name now, gauge fields or potentials. Usually when you do when you do just the classical elasticity theory, you introduce just a single function whose defined as sigma ij is di dj chi. It's an Airy function. It's the Airy function, stress function chi, which is like the electrostatic component of the gauge theory that I'm describing. I don't know if I answered that question completely, but I think I did. But
so sorry, I didn't quite get it, but maybe it's
so again, so if I want to solve this, suppose I'm doing classical elasticity, which is maybe more familiar, so I don't have any dynamics. I would want to solve divergence of sigma equals to 0 theory condition. The way I solve it is I solve it by this condition. 90-degree rotated, gradients of chi, double gradients of chi. So that's the way I would solve this equation. And now I would reformulate. Now I don't have to solve this divergence of sigma anymore. And now I can deal with defects in the rest of the theory in terms of this chi electrostatic potential. What would be an electrostatic potential in this gauge theory? So the redundancy is that I can, there's a redundancy in being able to add gradients, extra gradients of time derivatives of, I'm describing actually here, exactly. So that redundancy exists in the elasticity theory. It's just often not emphasized. But when you actually want to solve something, it appears explicitly. Okay, so this is the vector gauge theory formulation of elasticity fracton duality. Again, it's written in terms of 3 sectors. There's a flavored sector of E and A, capital E and A, and there's a non-flavored little e and A, and they're coupled through this minimal like coupling between them, and then they're sourced by the underlying charges, dipoles, which are dislocations and disclinations. The Gauss's law now become 2 separate Gauss's law, which are coupled actually. There's a standard Gauss's law for disclinations, for little e field, sourced by disclinations or fractons. And then there's a flavored Gauss's law for capital E and K in A, for capital E, which is sourced by underlying dislocations, dipoles, p sub k, but also this electric field is appearing inside the source. So the electric field lines that are produced by disclinations in the little EA gauge sector is a source of charges for the capital E theory. So there's this really non-trivial, I call it, minimal coupling, because it's really like coupling a gradient, a derivative of a 1 form to a 2 form. And there's a gauge. So now one can look at the gauge redundancy. There's a gauge redundancy that there's a standard redundancy of little a under phi, its gauge transformations. But when one gauge transforms capital A by a flavored function chi sub k, A transforms normally, but the little a transforms by that function directly. It literally just transforms, that function directly enters a sub k. And you can see that here in this theory. If A is shifted by grad chi, then what enters here is a curl of chi. That curl of chi can be absorbed into little a by actual shift of little a by chi. And one can count the space of Gage redundancy and convince oneself that this full redundant Gage space reduces to 3 degrees of freedom, 2 phonon modes and 1 bond angle that are coupled together. So 3 physical degrees of freedom. The other thing that one gets, which is quite beautiful, I should say, I will immodestly say that the fractonic nature is very nicely formulated in terms of continuity equation for dipoles. When one looks at the dipoles, the continuity equation is broken by the current of fractons or the current of disclinations. So if you don't have any dislocations around, then the current of disclinations has to be 0. And that's just imposed through Gage invariance. So in other words, if I take this Gage transformation here and apply it here to, enforce it onto this, then I will, this pseudo continuity equation emerges, which will say that J is 0 in the absence of dislocations. And the complement of that is if you have disclinations moving, they have to produce dislocations. And that's just a statement that I discussed before in the cartoon picture in the introduction, that motion of charges has to create dipoles. And because I'm running out of time, I'm not going to go over this, but needless to say, with Mike Hermele, we formulated a nice lattice gauge theory description of this, really in the same spirit as conventional gauge theories, lattice gauge theories, where it's a very well defined, and one can simulate this model and study it in great detail. There are 3 lattices one has to define. The black lattice, that's the underlying lattice, and then there's 2 other lattices, one corresponding to each of the flavor of the gauge fields. And by the way, in D dimensions, this very nicely generalizes to in D dimensions, you have D E sub k fields plus 1 E sub k E field. So it's nicely generalizes to D plus 1 coupled vector gauge theories. And I should say that the duality only works, we can only produce this duality, at least in this way, as an XY duality in 2 plus 1 dimensions. But once we produced the dual gauge theory, then it's very easy to generalize it to a D plus 1 dimensional theory and convince yourself that it still has fractonic matter. Again, I don't really have time to discuss this, but needless to say, not surprisingly, vector gauge theory and tensor gauge theory formulation as duality are completely equivalent, and they emerge. So tensor gauge theory emerges from the vector gauge theory in a low energy limit. So what does one do with this? Well, we've been having a lot of fun for the last couple of years studying this, and in particular, not just looking at the fracton phase, but one can look at variety of phases and the analogs of the crystal phases, namely supersolid phases, hexatic, superfluids, and understand how in the gauge theory, one transitions between these theories. So for example, one thing one observes is that there's actually 2 types of fractonic phases that one obtains, and they correspond to the 2 types of crystals one can have, a commensurate crystal and an incommensurate crystal, otherwise known as a supersolid.
So are these parameters in this plot, are they parameters in the continuum field theory or only on the lattice?
No, they're parameters in the continuum field theory, and I haven't explored their sort of strict, what the parameters are and how to control these, how to access these in the lattice model.
But isn't the continuum field theory just quadratic? I'm a bit confused.
It's quadratic
How do you get all these fascinating phases from a quadratic?
It's because it's like anything. So, if you just map XY, bosons, XY model onto you want gauge theory, then it's quadratic and there's nothing to do. But once you allow for matter and that matter is dynamical, in order to describe topological defect unbinding.
Okay,
then
so in that, but if you allow the matter to fluctuate, then it's not quadratic.
Exactly.
I think Leo's meant only that the field is compact. It's quadratic, but it's compact. Is this right? And then many transitions, of course.
So
I just meant that at the level where all the dualities were strictly speaking happening, they were happening at the level of quadratic actions where we could
exactly. So you're absolutely right. So what one needs to do to access this phase diagram, one has to elevate the matter, which just enters through J dot A. One has to elevate it to dynamical matter and really have an abelian Higgs analog of the abelian Higgs model. And then you're studying some kind of a funny normal to superconducting transition, where the matter are these dislocations and disclinations.
You mentioned, you said something fracton phases, but if it is a theory of elasticity, what phases are those that in the language we engineers who do elasticity understand?
Right. So strictly speaking, so the fracton phenomena only occurs in the crystalline phases. When you melt it into a smectic or a superfluid, then that fracton matter is gone. So this gauge theory then allows you to describe how you leave the fractonic phase. Okay, so indeed there's no fractonic nature here. It's just a quantum phase with conventional broken symmetry. So let me just go on. So the way one describes this is proliferating dislocations, and in the square lattice there are two types of dislocations, two flavors of that flavored vector gauge theory. Okay, but imagine, and so this is something we explored previously, but now I want to get to the kind of the punchline of this talk, or the new content of this talk, and that is thinking about other states of matter, and namely quantum liquid crystal states of matter. So and this is summarized in this flow chart. So imagine I want to get to a quantum smectic. I could get to it by first taking a quantum crystal, unbinding dislocations, X kind of dislocations, and thereby creating a smectic. And then I can elasticity of a quantum smectic, and then I can dualize that in the way I just described that I've done for a crystal to get a quantum smectic vector gauge theory. And that's a one path to it. The other path is to take the dualize the crystal, get a vector gauge theory description of this quantum crystal, and then have a transition. And that transition, that's just to let the cat out of the bag, is just going to be a Higgs transition of the Y dipoles only. And to contrast it to this picture, here I'm condensing both the X and the Y dipoles or dislocations, but imagine I only condense the blue dislocations, but not the green dislocations. And one can imagine having that if you have anisotropic system, anisotropic crystal. And so then what one gets in terms of a picture is a picture I already showed before. You have a quantum crystal, one can get to a quantum smectic and then study these transitions. So let me now describe how this is, how this emerges. So it's very similar story, in fact, embarrassingly simple story if you follow the one for the crystal, now just done for smectic. So take a quantum crystal, here it is, kind of a simple description of crystal. Here's the elasticity, here's the kinetic energy. These are canonically conjugate to each other. And what you do now is you condense only one type of a dislocation. And what you get is a super smectic that I described, that I illustrated here. And dislocations are indicated in these black little T's. Okay, so now that I have the dislocation smectic theory as a plasma of a crystal plus dislocations, just the X dislocations, then I can reformulate I would like to now dualize this elasticity of a smectic. So let me first write it down. So elasticity of a smectic is going to have the orientational bond degree of freedom, which is the 1XY model here for the theta. That describes the the bond angle. So if I have my smectic, there's a local bond angle describing how much it's tilted, theta, relative to the perfect state. Okay, so that's theta. And then in addition, I have the phonon degree of freedom, U, which is the single degree of freedom, which I call here UI, but I'll just drop the Y very soon. So now there's an XY model, a single XY model, but it's coupled to the orientational degree of freedom. And this minimal coupling encodes the information that if I have a smectic that's oriented like this, its energy is equivalent to a different spontaneous symmetry breaking smectic where I've rotated all the layers. So this is a global symmetry of the smectic, much like there was a similar symmetry for a crystal, for a quantum crystal. And so this is how this is encoded. In principle, there's also a sector, which I didn't discuss, which is of bosons. Once you unbind dislocations in the crystal, there's no possibility a pair of dislocations automatically create a vacancy interstitial or an atom or an absence of an atom. So therefore, if you condense the dislocations, you automatically are forced to condense. The atoms themselves are forced to condense. So in addition to whatever I'm going to focus on here, keep in mind sort of as a background, but not, sort of implicitly, there's also going to be another sector that describes the underlying XY model that describes the superfluidity or mod insulating behavior, but a superfluidity, behavior of the underlying atoms. And this thing will always be in a superfluid phase.
So this thing is why you're calling it a super smectic.
That's why I call it super smectic, because while for a crystal, there's a possibility of two types of crystals. There's a supersolid, which is an incommensurate one where vacancy interstitials have both condensed. And then there's a conventional commensurate crystal where in the ground state there are no vacancy interstitials, and there's a quantum phase transition between them. For the smectic, there's no such possibility, at least without a substrate. Okay, so then again, so here's my elasticity that I talked about of a smectic. I dualize it now by a very standard method, and what I get is I won't write down this part. So now I have a single gauge field because there was a single phonon here. That corresponds to capital E and capital A. And then there's a bond angle that corresponds to little e, little a. And then there's some anisotropic minimal like coupling between the two gauge theories. So it goes through just as the same, except the continuity equation now that emerges is only involves on the right-hand side. It's only broken by the X component of the disclination current or charge current. So what does it imply? It implies something that I wasn't aware of, even though I spent much of my career working on smectics, and that is that disclinations in the smectic, if you can create a pair of them, and I will show in a second, if you could create a disclination in a smectic, a motion of that disclination is not allowed along the layers. They can only move perpendicular to the layers. And so here's the microscopic picture of how you should think of this. So imagine I created two disclinations in a smectic, and it's just convenient for convenience. I want to think about two disclinations rather than one, because if you have a one disclination, it's tough to draw the layers. The layers will completely be turned by 90 degrees. So you have two disclinations, and they're separated by few layers apart. They have some non-elementary dipole moment. And so one can ask, what happens if one tries to move one disclination relative to this dipole, relative to the negative one? And in fact, that's one can see here microscopically, that's an impossible process in the elasticity theory, as this is a non-local process that requires an insertion of multiple half layers of atoms, which is a non-local process. It's not an operator that will be available in a system that's local, in a Hamiltonian that's local in terms of atom degrees of freedom. Okay, so that's not allowed, and in fact, that's what the vector gauge theory in fact captures. So it very economically summarizes those constraints, which are quite non-trivial to impose if you had any other sort of the elasticity level formulation of the smectic. One additional consequence of this is one can look at the hydrodynamics, and that hydrodynamics is anomalous. In fact, if you look at the continuity equation of the two continuity equation, one can combine them and solve them by Fick's law. And lo and behold, I'm rushing through a little bit because of running out of time. But what emerges is a continuity equation for the charges. But that continuity equation, relaxation kernel gamma sub k, is normal in the y direction, perpendicular to the smectic layers, but it's anomalously slow along the smectic layers, and that just encodes these continuity equation, coupled continuity equation. So now, I've set all this up, and now it's very simple to explain. And in fact, come back to Michael's question about the phase transition. So now that I understand the phase, I can think about the phase transitions. So let's think about a crystal to smectic phase transition in this dual language. So here's our dual gauge theory description of a quantum crystal, this guy. Now what I'm going to do is I'm going to elevate the matter to be dynamical, and the way that's done is, the way one can do this is simply couple this Maxwell gauge theory, Maxwell sector of the gauge theory, to matter, and that matter is flavored describing the dislocations. So there's a psi sub x and psi sub y for the two types of dislocations, plus there's a Maxwell sector here. Okay, so now it's very simple to see what happens if one condenses one flavor of these dislocations, namely condenses y dipoles or x dislocations. Then what one does is makes this psi sub y condensate, and that Higgses out the one of the two flavor gauge fields, a sub k. It just Higgses out a sub y. And so then what one obtains at the lowest order description is simply that the quantum smectic gauge theory is really just the quantum crystal gauge theory description with a sub y set to 0. That's kind of to lowest order, where you can just integrate out the a sub y gauge field corresponding to the y dipole matter that you condense. And indeed, lo and behold, what emerges is the Hamiltonian that we derived by duality previously, as it must. But now one can go one more step. One can take the quantum smectic and see if one can quantum disorder the quantum smectic. And that's, again, quite simple. It disorders into a nematic if one want to go through a continuous phase transition. So here's a gauge theory of a quantum smectic. One elevates the matter, the remaining matter, into dynamical matter. So then what one gets is a Higgs model, a Abelian Higgs model with a strange Maxwell-like action. So this Maxwell action is just this two coupled gauge fields, as opposed to conventional Maxwell action. And so now one condenses the X dipoles as the second step in this process. We've already condensed the Y dipole, so now we're going to condense the X dipoles. Condensing it, then this now gaps out the AX gauge field, Higgs is out, and what one gets is a simple model just for the remaining little e gauge field, for this gauge field. Since capital A has now been Higgsed, then what one gets is a simple abelian U1 vector gauge theory, which is just described here, coupled to the remaining disclinations of the remaining charges. And indeed, not surprisingly, this is just a dual of the rotor model of the rotational degrees of freedom of the smectic, and that's really describes the nematic. That is the nematic. If I had to write down a quantum theory nematic, it would be just this rotor model, and it would dualize to this. So this is gratifying to see. But now we really have a full description, quantum mechanical description of this transition with defects and quantum dynamic description defects. So with this, let me summarize and mention some open questions. I talked about fractons, elasticity, duality as realized as defects in the crystals in the smectic. I described for you an anisotropic type of state, an anisotropic transition into it from the nematic and crystal. And this is summarized in this figure. And there's two ways of getting to this quantum smectic that I described, either by dualizing, melting and dualizing, or by first dualizing a crystal and then having it undergo a Higgs transition. There's a number of questions that we're grappling with now still. So one thing that I described is kind of a me-field description. We have not addressed the actual criticality of this quantum phase transition. So this is the analog of asking, what's the analog of this funny superconductor normal transition across here, or abelian Higgs transition across here and here, with this new type of a Maxwell term that I've described here. So now there's a new type of a Maxwell term. And so the question is, what is the nature of that transition, abelian Higgs transition? So that's one open question. I'm sure it's very, very well accessible. The other question is that one can think about is quantum Hall smectics and everything. Although I use those as a motivation, nice physical motivation for thinking about quantum smectics. Those smectics break time reversal symmetry, but everything I've written here is time reversal invariant. So although I have a sketch of I have a formulation of a quantum Hall smectic, there's a lot more to explore about it. So to repeat this for the quantum Hall smectics, there's a question about commensurate smectics that in principle can appear if one has a substrate. And finally, one thing that I ignored that is known in elasticity of smectics is non-linearities. Everything I've done is in the harmonic theory of the elasticity, and therefore the Gage theory comes out to be a quadratic theory. But it's known that in the smectic, non-linearities in the presence of fluctuations can be important. And so the question is, can this be extended to include those non-linearities? So with this, I will close and thank you for your attention.
Great, thanks a lot. Let's thank Leo for a nice talk.
Thank you.
So we can take still a few questions.
I had one quick question.
Leo?
Oh, sorry.
Yes.
Go ahead.
I was just wondering if there are any sort of non-abelian generalizations that are possible or that one could imagine. By that, I mean the Gage group, not being U1.
Well, one can imagine it, but the thing that I can say unequivocally that it has not been explored, certainly not by me or others. But that's another direction that one can consider. That's very interesting.
Leo,
Yes.
can you tell more about the effect of non-linearities? Are these just in the Gage theory, just terms that are nonlinear in fields?
I don't know. Well, so it's an open problem. I don't know how to execute this duality in the presence of nonlinearities. And so let me just for a second write it down. So naively, a smectic is described by, well, so the simplest description of a smectic is just, sorry. So at a harmonic level, that's what a smectic looks like. So you have a layered, if you have a layered rotational invariant, if you have a layered state that spontaneously breaks rotational and translational symmetry, then this is its elasticity. And the reason is, this encodes underlying rotational invariance between these two states. The fact that it's broken spontaneously. This is to be contrasted with a charge density wave, for example, like unidirectional charge density wave. But it's known that this is not enough. In fact, full elasticity of a smectic is actually, so this is invariant on the small angle rotations. So in other words, this theory is invariant on the theta times x, global, well, you can call it global or local, this non-trivial transformation on this train, on the displacement. So this is describing the rotation. And you can see here, this Laplacian ensures that there's this invariance is encoded. But this is only true for theta much less than 1. But suppose you want to write down fully nonlinear theory that is rotational under full rotation, then you need to include nonlinearities, which look like. So what one needs to include is a fully nonlinear strain tensor.
Mhm.
And so, and these nonlinearities in the smectic, at least in a thermal smectic, well, in the thermal smectic in below 3 dimensions, lead to breakdown of Gaussian description. They really give you a non-trivial fixed point that describes a smectic, at least a classical smectic. So this is temperature. There is some fixed point that describes, you know, let's say 2D smectic. And it's a non-trivial infrared attractive fixed point. So that means in no sense is this Gaussian theory enough in 2 dimensions. So now one may ask, what is the role of this in a quantum 2+1 dimensional theory of a smectic? But in particular, and you know, indications are it's not important at long scales, but one can still ask, can I execute this duality in the presence of these nonlinearities? And I don't know how to do this.
Thank you.
Can I ask about the critical? You had a point on the critical transitions.
Oh yeah, sorry.
Wouldn't you expect them to just be the BKT or rather Halpern-Nelson type universality, or do you think there's?
Where you mean these transitions?
Yes, or whatever you meant by your first point, I guess.
No, I mean, this is a quantum theory. So Halpern-Nelson stuff is, well, there's a lot of, you know, sort of counterparts of this that's been studied by conventional methods using Coulomb gas-like descriptions. And we've done a theory of this in terms of vector Sine-Gordon models with multiple charges. But this is all 2-dimensional classical thermal transitions. Mm-hmm. So what this gives you access to is a quantum 2+1 dimensional transition. Mm-hmm. So that's not been done to my knowledge before. Mm-hmm. And so, yeah, and so we don't understand the nature of these transitions yet. We just, you know, what I gave you is kind of a, if you wish, a mean field description, which produces the phases. This is that Higgsing where I set some flavors of the gauge field to 0 by Higgsing.
Mm-hmm. Yeah, general question about this gauge theory gauge description. I never heard that it's possible for elasticity, but I do remember the Gen gauge description of smectic. You must be familiar.
Yes, so what's the question?
Is this gauge symmetry you have in mind? Those which the Gen, I don't know, 50 years or 40 years, 50 maybe years ago, described for smectic? Not for crystal, but for smectic.
Yeah, so in fact, indeed, there's a de Gennes model of the smectic. So, so there's a standard model. So this is de Gennes model of nematic smectic transition, and it's described by, so de Gennes proposed it. It's described by an abelian Higgs model. It looks, in fact, very much like normal superconducting transition. It's, you know, grad minus I Q naught delta N. Oops. You know, V of psi plus, you know, Frank free energy, which is, you know, curl of delta N, roughly speaking. Okay. Actually, well, it's important to say it's actually not curl. It's actually
that, you know, is known what it means.
Yeah, there are terms like this and there are terms like this, roughly speaking. Okay, so in fact, this is the de Gennes model of the nematic to smectic transition of the thermal transition, and this is a transition where you go from a nematic phase where you have just a nematic elasticity and that's it, where you develop psi, where psi is the density wave. So if you know, if you have a nematic, here's the nematic. What psi describes is is emergence of a periodic modulation on the density of these molecules. This amplitude is psi. Okay, and the phase of that psi are the phonon degrees of freedom, are displacements of these layers. So these is the, so psi is, psi magnitude e to the I q naught u, where u is the phonon degree of freedom. So indeed, that's the Duchenne model that describes thermal phase transition from a nematic to a smectic, indeed.
Yes, but my question is, the gauge theory which I'm still missing, but you spoke about it, is this a similar gauge symmetry which emerges?
No, it's completely different. This is a transition from a disordered phase from the nematic into a smectic in terms of conventional sort of Landau order parameter condensing, which is the condensation at a finite wave vector of a mass density wave of these molecules. What I'm describing is going in the other direction, where I'm going from where, if you wish, it's a dual of this theory. But it's also quantum. It's a theory that has all the Berry phase physics describing the how topological defects behave and statistics of topological defects, which are and how they couple to the underlying gauge field. So it's not this theory.
So I'm not asking about theory, but so you're saying that the gauge transformation or the symmetry, local symmetry, which is pretty obvious is in smectic.
Right.
This is one thing. No.
So
and
there's no
the gauge transformation, I'm sorry, of what you describing, are they similar? Are they applied to the same?
No, they're very different. So they're very different. So this gauge theory, one can call it a gauge theory, but in fact, it's a gauge theory in which what we would normally think of as degrees of freedom that are not gauge invariant are actually physical. So in other words, a smectic has degrees of freedom and a nematic have degrees of freedom. If you think of this as a gauge theory, smectic and nematic have degrees of freedom, namely psi and n, which you would think of as a vector potential, which in fact are physical. For example, I can tell you, the phase of this psi is actually the phonon mode and the displacement of the smectic layers. And the gauge field corresponds to the director reorientations. So it's like being able to study gauge theory in which there's actually no, the gauge degrees of freedom are one, are physical, and two, they actually cost energy. For example, there's actually an energy cost for splaying molecules. Like if you take the molecules and you splay them like this, they will have a non-trivial divergence. And that costs energy. And so indeed, there's an energy cost for divergence of n in this Duchenne's gauge theory, so of description of the nematic smectic gauge transition. So you can call it a gauge theory. You can learn a lot by thinking about normal to superconducting transition, Ginzburg-Landau theory, but you have access to many more physical observables, which you would otherwise in other contexts call not gauge invariant and unphysical. So my theory has nothing to do with this. For one, it's quantum, so it's in 2 + 1 dimension. And two, my psi is kind of dual to this psi. It's the dislocations in this psi degree of freedom. So you can think of my psi of vortices in these psi. That's actually a good question. That's true.
So maybe we can talk about this more in the discussion session. So let me just stop the recording.